Well, good evening and welcome to AP Physics or AP Live tonight. You're tuned in to AP Physics C, Electricity and Magnetism. My name is Roger Siegel, and I am coming to you live tonight from Sarasota, Florida. And we are hard at work getting ready for our AP Physics C E&M exam, which is next Monday, the 11th of May. And depending on where you live, you'll have to check the times. And tonight with me, as always, is my good friend and co-teacher, Kristen Gonzalez Vega.
Hi, Roger. It was kind of weird not being here last night, so it's nice to be back. I'm Kristen Gonzalez Vega, and I teach in Frisco, Texas.
All right. Well, thanks so much for as I said, for joining us. If this is your first night with us, tonight's going to seem really strange because we're going to pick up right in the middle of something. But remember, all of these videos that Kristen and I have been making since March are all archived online. You can binge them this weekend as you're getting ready for the exam. But if there's anything that you need time with, you can just pause and come back to it. The recording will be here. All right, great. Well, we are going to start where we left off last night. I'm going to share my screen with the world here, and I'm going to pull you over to here. And this is how we started yesterday. Welcome to AP, to Prep Week. And so all this week on your live AP channels on YouTube, we are giving you mocks. And so here on our channel, Monday night, we gave you 2 questions, a 30-minute and a 25-minute question and a 15-minute question, and hopefully you worked on those. We're going to go over those questions tonight. Tomorrow night, we're going to do the same thing again. When you tune in tomorrow night, there's going to be a timer and 2 questions, and let me show you what that looks like. Okay. And by the way, let me stress this point because it is important. While the questions that you're going to see tonight and this week are designed to be similar in structure and format to what you'll see on the AP Physics C, they are not intended to be representative of the content. Okay. The content is much wider, much more than we can cover in any of these. So, but the form, the style, that's what we're trying to get you to see. Okay, so this is what you would have seen had you tuned in last night, except you would have seen these numbers tick-tocking away. And what happens is this timer counts down to 5 minutes, and then it turns red, and then it counts down to 0. And so last night we simulated you trying out a 25-minute question followed by a 5-minute upload. Now we didn't do the upload, but before we leave tonight, I'm going to show you where you can practice that. Now, this website is where you can go to get copies of the problems that Kristen and I are going to be sharing with you this week. And so we want you to go to those sites and to print these out. And if possible, if you know you're going to join us at 6, go ahead and log on, 20, 30 minutes early. You probably can find this, or actually this is open now all the time. So if you go to this folder, you will find the problems, and they're labeled Monday mock question 1, Monday mock question 2. So here's question 1 and here's question 2. And so, and they're both at this address. And so I'm going to first work through this problem with you. The first one, and this is the 25-minuter, and then Kristen is going to work through the second one, the 15-minuter, and then we're going to talk more about the exam, and then we will send you home. Just sign off. All right, let's take a look at this. I'm going to actually, it looks like I've already started my notes here, so I'm going to restart this. All right. And let's take a look at this question. Now, first, it says at the top that it's approximately a 25-minute question. Read each of the parts carefully. Support your answers with relevant physical principles. The parts within each question may not have equal weight. Write your answers in the parts provided after each part. You will not find, if you find that you are in need of symbolic notation that is too difficult to type, you may identify a non-standard symbol and use that throughout your answer. For example, you may identify Q as the measurement for an angle. Now, Folks, this is why we want you to practice this, because you're going to want to decide before you sit down to take the AP exam next Monday. You're going to want to decide, am I going to want to type it or am I going to want to write it? Because you have that option. And some people are much more comfortable writing. You can take a picture of your writing and upload that. Some people are much more comfortable typing. And so we really like you to have a chance to try a few of these different formats, see what's most comfortable for you, because we don't want you to have to fret or have this be the first experience when you are logging in, when you're on the clock and taking the exam on Monday. All right, so those are the instructions. Let's look at the problem. So the problem provides us these two diagrams, the picture and the graph, and it says a large non-conducting sphere of radius r equal 10 meters is fixed in space and carries a spherically symmetrical charge distribution. The sign and density of the charge distribution changes as a function of the radius r from the center of the sphere, represented by rho of r. A hole extends from one side of the sphere through the sphere's center and to the opposite side of the sphere. A small non-conducting ball carries a positive net charge and is placed within the hole. The location of the ball is x. The friction between the non-conducting ball and the sphere is negligible, and the ball does not exchange charge with the larger sphere. The graph shows the electric potential V of R at points in the hole between the center of the sphere, R equal 10 meters, and the right end of the sphere, R equals 0 meters, and the right end of the sphere, R equal 10 meters. So here's our sphere. It's a big old sphere. It's 10 meters in radius. And so this graph shows us starting at R equals 0. This is the center of the sphere, and this is the outside. So you can see that this is the center right here, and this is the outside, and this graph takes in all of that. All right. All right, let's look at the first question. And I'm going to be, kind of going up and down so you can continue to see the pictures. And so the first question says, what is the farthest point from the center of the sphere from which the ball may be released from rest and exit the sphere? Justify your answer. What is the farthest point from the center of the sphere from which the ball may be released from rest and exit the sphere? Justify your answer. Well, if you looked at this this graph and said, this seems a lot like a potential energy problem, where we have U of R as a function of position. And I think these were probably more prevalent in the AP Physics C mechanics, if you took that, but we had a lot of U of R versus R. And so you look at this and go, well, wait a minute, that's not U, but remember that U is equal to QV. And so if I just were to multiply this by Q, I would get U. In other words, the difference between U and V, between potential and potential energy, is a constant. So that tells us that even though this is a potential curve, it acts and behaves exactly like a potential energy curve. And so we're going to treat it that way. And so what is the farthest position from the center of the sphere from which the ball may be released and exit the sphere? Now we know it's released from rest. Now, if we look over here, exiting the sphere exit has a potential of 60 volts. So if I release my object from here with a potential of 40 volts, the furthest it can go is over here. I've got to release it with at least 60 or more volts. And so the answer to what is the farthest from the center, the farthest is X equal 2 meters. Okay, and now why? Why is that? All right, so here's what we're going to say. Now, you just can't jump and start talking about potential energy because you don't have a potential energy graph, you have a potential graph. So we're going to say since U is equal to Q delta V, or QV, the potential energy is proportional to the potential. So now you've just told the people who are grading your test, I know that this acts like a potential energy curve. All right, so that's the first thing. Then the second thing we're going to say is due to conservation of energy. If you are using conservation of energy, you should say it, because that is something that we're always looking for in AP Physics, is the big ideas: conservation of energy, conservation of momentum. So due to conservation of energy, okay, if the initial potential is greater than 60, volts, comma, the ball will exit the sphere overcoming the maximum exit potential of 60. Okay. Now, I'll have to ask, but I think we should be able to upload the rubric to live in this tiny URL right next to the problem. So I'm going to look into that. I don't think it's there now, but I'm going to look into putting that there for you guys. Okay, so that's the answer to part A. Let's look at part B. Okay, part B says the ball is released from the position indicated in A. So that's the farthest to the left that it can be released. And so I'm going to release it here. Let me go ahead and erase this so we can see that. And so I release the ball here, right there. Okay. And so, and it exits the sphere. Describe the magnitude and the direction of the ball's acceleration between 5 and 10 meters, the ball's acceleration. Okay, so how do we get acceleration from a potential curve? Well, there's a couple of ways to look at it, but I know that acceleration is equal to F over m, or 1 over m times F. And so that means acceleration is equal to 1 over m times, what is the force? It is the negative du dr. Now, what is u? Well, A is equal to 1 over m times negative ddr. And what is u? It's qv. So I can pull the q out of the out front, and A is equal to q over m times the negative derivative of v. All right, now let's look at this graph. Here I am from 5 to 10. Here is v. The derivative of v is positive, so the negative derivative is negative. So what I'll say over here is, since A is equal to negative q over m dv dt, and dv dt, I'm sorry, dv dr, not dv dt. Let me fix that. And since dv dr is positive, let's look at the slope over there. You can see that the slope of the graph here is positive. So since A is equal to negative q over m dv dr, and since dv dr is positive, A is less than 0, A is negative, and so A points leftward. So that's the direction of A, okay? Now we've got the direction. Now what about the magnitude? Well, since since dv dr goes from 0, and so I'm saying the derivative or the slope of v with respect to r. And so let's look at the slope of this. And so here the slope is 0, and here the slope is 0, and here about 7.5, the slope is maximum positive. So what I'll say is, since dv dr goes from 0 to max positive to 0, comma, acceleration goes from 0 to max negative to 0. So we always want to be chaining those ideas together from one to the other so that we're showing the person who's grading our exam that we know how it all fits together. It's about just demonstrating our knowledge. Think about the person who's reading your test. They want to know, do you understand it? And can you show me that you understand it? All right, let's look at part C. It says a student's wishing to model the electric field within the hole for 0 to 10 suggests the equation E of R is equal to A times the quantity B minus R, where A is 4 volts per meter squared and B is 5 meters. Consider positive values of E or R to be directed rightward. State one feature of this equation that correctly models the electric field within the hole. Justify your answer. Now, this is why if it were me to choose, I would not choose to type, I'd choose to write, because I have to graph this thing. And so I'm going to write for part C, I'll come down here, that E of R is equal to 4 quantity 5 minus R. All right. And so what does that look like? Well, that's actually a straight line, ladies and gentlemen. And it goes from here, from the positive value of 20 to 0 to the negative value of negative 20. And that point is right there, 5. Now, that is my E field. That's E as a function of R. Okay, now we know that V is the negative integral of E dot dr. So ladies and gentlemen, what do you get when you take the integral of a linear function? Well, you get a quadratic. And this quadratic, you'll see, has this particular function is, if I'm going to integrate this, I would have a positive value or a positive slope and a 0 slope and a negative slope. But look at my negative sign. And so the solution to this equation looks somewhat like this. It is a downward opening parabola with its 0 at 5. Now, I'm sorry, I said downward opening, and that is completely wrong. Let me say why that is. Positive, 0, negative. So that would mean, yes, so that would be positive, 0, negative. And we're doing the opposite of that. We're doing negative, 0, positive. So there's my E field giving me my potential. And so what am I going to say about that? Well, I'm going to say that, remember what the question is. That's always the question. It says, state one feature that correctly models the electric field within the hole. Well, let's look. We know that the electric field within the hole looks like this, right? Let's go up there and look at it for a second. The electric field within the hole looks like this, okay? And I've got something that looks like this. It's close, right? So when we're answering the question, what feature correctly models the electric field? What I'll say is E is equal to 4 times 5 minus R is correct in creating a potential that is maximum 0 maximum. In other words, it has this maximum 0 maximum. And so with this picture, I feel like I've shown the graders what I've got there. And so that is one thing that it does have in common. Now, what is different about it? It says state one feature of this equation that is not correctly modeled. Okay. And so let's take a look. I think you can see it, but I'm going to go ahead and erase this so you can see a little bit better. All right. And so look at this. I've got a model that looks like this. Okay. Now look at this graph and tell me what's different. Well, look at this. We've got a lot of things going on with concavity. This is a concave down function, concave up, concave down. The parabola is concave down everywhere. So what I'll say about part D is I'll say the equation fails to model the up, I'm sorry, it starts with down, the down, up, down concavity of the actual potential. All right, so it fails to model that, and so it does not replicate it. So that's my answer there. All right, we're almost there, folks, and you've been hanging in there. Proud of you. We're almost there. Sit tight. We're going to get to the next one in a minute. All right, explain the steps that a student must follow in order to derive rho of R from E of R. Well, we hope that all that work we did in previous previous days with Gauss's law is going to pay off for you, because we think that that's where you'll find it. So Gauss's law says E dot dA is equal to Q enclosed over epsilon naught. So how do you do it? One, begin with Gauss's law. What do you do next? Well, you're going to find the Q enclosed. So the Q enclosed is going to be multiplying every differential volume, every tiny, very, very thin skin that I can put on this sphere, right? It's going to have the density function times the surface area, 4 pi r squared, times the thickness of my area of my volume that I'm painted on here, and that's dr. And so that's my Q enclosed. So I'm going to rewrite this as the Gauss's law, the closed surface integral of E dot dA is equal to 1 over epsilon naught, the integral of rho of R times 4 pi r squared dr. Now they just say, you know, how do you do this? So we're going to find enclosed charge. That's what we did here. Okay. The next thing is just algebra, so I don't think we need to say that. And so we're going to solve for rho, because that's for rho of R. And so I'm going to go ahead and do Gauss's law over here. Well, I know that I've got a spherically symmetric charge distribution. I'm going to choose a spherical Gaussian surface, which means we have perfect symmetry. And so I can pull the E out of the integral, as we always do with Gauss's law. And the area is going to be 4 pi r squared, because that's the area, the surface area of a circle. And so that's going to be, and let me go ahead and multiply this, because this is going to be E as a function. Let me write this differently. This is E as a function of R. All right. If you didn't write it that way, that's still okay. But now what do we have over here? Well, let me go ahead and multiply by epsilon naught. And so I'll have epsilon naught, and that's equal to the integral of rho of R times 4 pi r squared dr. Now, how do you get the rho out of the integral? Well, you unintegrate. And what is unintegrating? It's taking the derivative. So I'm going to take the derivative of both sides. I'm going to say take ddr of the quantity E of R times 4 pi r squared epsilon naught, oops, is equal to rho of R times 4 pi r squared. And so finally, we have rho of R is equal to 1 over 4 pi r squared times the spatial derivative ddr of the quantity E of R times 4 pi r squared times epsilon naught. Now, If you wanted to, you might see I could pull out the 4 pi and that can go away. Those are constants. The epsilon naught can come out. But you can't pull these two out because they're functions of r. But you could leave the whole thing like that. Now that last part, ladies and gentlemen, is a 5-pointer. I think this problem shows me that I would probably be better to be writing with longhand than typing. I don't think typing is going to be my best shot for this exam. Okay, don't know, but that's where I am. Let's see, do I need to write anything else? So solve for rho of r, and we get that. So that is what we have, ladies and gentlemen. So as I said, we're going to try and put those solutions up for you, but we hope that that gives you a good sense of what we're looking for in these problems. Remember, not specific the content. The content is certainly important, but the style. All right. All right, Kristen. Do you think
Yes, we're
they're
ready
still
for
with
number
us?
2. Hopefully, yes. I
All
think,
right, take it away.
all right, we're going to look at number 2. And as a side note here, the good thing about the exam this year is that you get to pick which way you're going to upload, like you said, Roger. I think I'm going to be a cut and paster because I don't want to worry about my image being blurry and stuff, but you also can pick from one question to another. So if you get to question 1 and you've set in your head that you're going to be a copy paste person, but you see the problem and you think you probably want to maybe add a diagram or something to your explanation, then that's fine. And then you get to question 2 and it's all just wordy words and you want to copy paste that one. Those are 2 separate things. So you can do a picture for question 1 and you can do a copy paste for question 2. You cannot mix within one question though. So I can't want to upload a question for part A of number 1 and then copy paste for part B. It's got to all be in one thing. So we're going to look at number 2 here. And number 2 is our experimental problem, our 15-minute problem. And that is to determine the internal resistance of our battery. So just a real quick overview of the question. We have a group of students wanting to experimentally determine the internal resistance of the battery using the circuit shown above. The battery is assumed to have an internal resistance of R and a constant EMF of E. The students are expected to find the internal resistance by plotting their data in a graph. The students have access to equipment including, but not limited to, a variety of resistors, multimeters, and other equipment commonly found in a high school physics laboratory. So first thing I want to point out here is that we want to plot our data in a graph. What does that mean? That's their way of telling you you're going to take multiple trials, right? And that's something we always want to do anyway. So we're going to kind of maybe make a list here of things you want to keep in mind when you're answering a lab-based question, because we will have one. Okay, so that's not really number 1 though, so we're just gonna put it in the back of my head and we'll put that down here in just a second. The first thing I always want you to do though is I want you to think about a relationship. So even though this is gonna be wordsy and it's gonna be explaining, it still comes down to what's going on, and we can still, if we're going to be creating a graph, it's gonna come down to a relationship. We graph relationships. So if you are going to be creating a graph, you want to think about, well, what relationship could you use to describe your situation going on? So if we have a circuit, well, what can we do? We can always write a loop rule equation. So before I even try to get ahead of myself and what I'm going to do and what am I going to graph and what am I going to measure, well, let's start with the basics and what is your relationship. So let's write a loop rule for this situation. So we have a battery, it has an EMF of E, and we have the internal resistance of the battery, and then we also have a resistor in our circuit. So if we're going to write a loop rule, well, remember our potential gains have to equal our potential losses. So the gain of the battery, the EMF of the battery, has to equal, well, the potential difference from the internal resistance, which is going to be I times little r, plus that potential difference across resistor R. So that would just be I times R. And you can write this different ways. The way that I kind of think of it, if I know it has internal resistance, I like to automatically just put my equation in terms of terminal voltage, because really what is the EMF of the battery minus that potential difference across that internal resistance? Well, that is, we call that terminal voltage of the battery. What voltage is actually getting to your circuit. So you could use this equation. You could simplify it to I times little r plus big R, or what I really did is I just put it in terms of the terminal voltage. So I said that EMF minus IR equals VT. So this is the one that I'm going to really use. But a lot of times with a lab-based equation, there will be multiple ways that you can do it or approach it. So settle into the way that you want to do it, right? So the first thing we want to do is we're going to determine our relationships, because that's going to guide us the whole way through the problem, right? So I've determined my relationships. It's the EMF of the battery minus that IR equals VT. Okay, so if I'm trying to find what that internal resistance is, we want to know what are some other things we want to know? What are some things that we could measure, keeping in mind that we need to plot a graph, so we need to have multiple trials. I'm going to go ahead and put it down here. So what things can we vary, and what things are constants? Right, so I pick my equation, I identify, well, what are the variables in there? What are the constants in there? What things can I measure, and what things would I have to calculate or that are constant? So in this circuit, we have a battery EMF. We only have one battery. It is not a variable power supply. And so we have a set EMF here, right? A constant EMF. Okay, but I do have a bunch of resistors that I could use. I could switch them out, or I could add, whatever. There are multiple resistors that I could use. So if I change that resistance in my circuit, not the internal resistance of the battery, because that is a set also. But if I change the resistance of my circuit, well, that's going to change the current in my circuit. And that's also going to change what that potential difference that I end up getting, or that terminal voltage, is. Right? So now I know what my variables are. So now I can think about what equipment would I use to be able to measure these things, and where would I measure them? How would I use them? Right? So let's actually get into the meat and potatoes of the question. So I'm one of those people, I like to kind of analyze everything that's going on before I really get to the question, because then I'm kind of ready to go already. So we want to clearly identify each quantity to be measured, the symbol used to represent the quantity, and the equipment that would be used to measure the quantity, right? So again, we're kind of already there. We know that our variables that we're going to need to measure is I'm going to measure the current. What do we measure current with? An ammeter. Okay, so we're going to measure current, and then I'm going to put in parentheses I, with an ammeter, and we're going to measure the terminal voltage. I'm going to shorthand this for you guys. VT, what do we measure that potential difference with? A voltmeter. They're not asking you here how exactly you're going to do that. They're just asking you, what are you going to measure, and what are you going to measure it with? Okay, you don't have to go into how you're going to do it in series or parallel, anything of that. Just keep it short and to the point of what they're asking you, because chances are they're going to elaborate it later on these lab-based questions. So the first part is just, what are you going to measure with what are you going to measure it? So we're measuring current with an ammeter, potential difference with a voltmeter, or the terminal voltage with a voltmeter. Part B, describe the procedure to be used to determine the internal resistance of the battery. Provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. That's big. As needed, use the symbols defined in Part A. Okay, so we want to think about an experiment that we could do to measure these things, and a way that we could reduce the experimental uncertainty. So the ways that we can, the easiest way to reduce error is this, by doing multiple trials. Not multiple trials of the same thing. You got to change one of those variables, right? So we're going to do multiple variables, or multiple trials, changing the current. How do we change the current? By changing the resistance. So what I'm going to do is I'm going to change out that resistance. So I can either add more resistors to the circuit, or you can just switch out if you have different amounts of resistors, right? So we're going to set up the circuit. Again, you don't have to go into a whole connect the battery and series. It's already set up in there for you. The diagram's already there. They just want you to describe what are you going to do with it from there, right? So we set up that circuit. We're going to measure the current, right? We've already said that current is I, so I can now still use I. Measure the current through my resistor R in series. That's important to say. We measure current in series with my ammeter, which that may be a little bit repetitive, but we just want to make sure that we're crossing all our T's and dotting all our I's. And that terminal voltage across the battery, or you could do it across the resistor, right? Once we're talking about that terminal voltage, that should be the same. You can measure that terminal voltage across your battery when it's in the circuit, not when it's out of the circuit, because that's the EMF. But once you place it in the circuit, now that becomes the terminal voltage. Or you can measure it, the potential difference across the resistor. Those should be the same. Across the battery in parallel with what? With a voltmeter. And then what are we going to do? We got to find out how we're going to do those multiple trials. And I'm going to change the resistance of my resistor and remeasure that current and that potential the terminal voltage. So you could either add more or change out, switch the resistance out, change resistance and measure new I and VT for maybe 5 resistances. Okay, so what are you measuring? What are you measuring it with? How are you going to vary your trials? And that will make a good procedure. Okay, next, which quantities, raw data or calculated from the data, would be graphed on the X and Y axes to produce a graph that could be used to determine the internal resistance of the battery? And so that's why I think that like my loop rule using that terminal voltage is kind of the easiest, or I think this one too. But again, there are different ways that you could do this, different things that you could graph that are going to be acceptable. But we're going to stick here with my equation. So I want to look at this and I can see it's already starting to mirror an equation for a line, right? We want this to be something that I can produce a graph to determine the internal resistance, which means I want it to be linear. I don't want to have some exponential that I'm going to try to calculate something from, right? We don't have those relationships anyway, but I want it to be a straight line. So I want this to mirror y equals mx plus b. Okay, so what can I graph? Well, I've already kind of got my y equals mx plus b here, just kind of written in reverse. I could rewrite this to be Vt equals my IR and my EMF. So I could look at that relationship and I can say, oh, well, what am I going to graph on the horizontal? I'm going to graph what matches up with my X variable. And really, I should write this XM instead of MX. Let me erase that and change that. Or R times I. Okay, so what am I going to graph on the vertical? I'm going to graph the terminal voltage. What am I going to graph on the horizontal? The current. And what is the slope going to be equal to? Oh, that's going to be equal to my internal resistance. What is the y-intercept going to be? That's going to be the EMF of my battery. So we're going to graph VT on the y-axis and current on the x. That's all I have to do for this part, right? It just says, what would you graph in order to determine that internal resistance? And then in part D, you're going to describe how you're going to use that information. Well, I take the slope. We got to do that first, right? Find slope of line, which is equal to the internal resistance. And y-intercept equals EMF of the battery. right? So I don't have to do any crazy math. There's some other ways that you do this where you've got to use reciprocals and things, but I think this is kind of the easiest way to go about it because I always want to try to find a way where my slope is just equal to my variable that I want and I don't have to do much with it. Okay, after completing their calculations, the students begin to consider the factors that might have produced uncertainties in their results. This is another also common thing, whether they ask you to come up with what some uncertainties might be, or they tell you this happens and you've got to say why. This is something that you always need to be thinking about. The students realized they did not take into account the resistance of the wires used to connect the circuit. Briefly describe how this would affect their calculated value of the internal resistance of the battery and explain your reasoning. So hopefully you guys saw this and you recognize that we've done this a lot. We did it more with like maybe our meters weren't ideal, but we tried to incorporate a lot of this when we were talking about circuits and uncertainty. So this time though, we didn't take into account the resistance of the wires. So we need to say, well, what would adding those wires resistance do? Well, if my wires have resistance, that means my equivalent resistance is greater, right? So when I found that internal resistance, I thought that was just the battery. So really, the resistance R from the graph is equal to the R of the battery plus the R of the wires. So what does that mean about the internal resistance of my battery? It's actually less than what we had found in the experiment because we have to take into account those wires resistance. Okay. So we want to just make sure on these labs again that you are trying to see what relationship you could use for that. How would you be able to vary variables in there? How would you find those constants? What's significant about the slope or the area or the y-intercept? And make sure you're saying what equipment you're using, what you're going to measure with that equipment, and then what you're going to do with it. So that's a lab-based question. The only thing I want to say before I hand it back off to Roger to wrap up tonight is tomorrow we've got another 2 questions that I'm going to proctor you through. I want you to make sure that you are bringing everything you need to pretend this is the actual test, right? So we'll do minimal instructions before because Roger did a really good job at explaining all that stuff from College Board on Monday. I'll touch on it again, but really we're just going to get down into it and do some practice. So bring everything you need just like it's next Monday. So have your formula chart. If you've started taking any notes or anything that you know you want to have on exam day, I do suggest that if you're going to do that, you keep it short and sweet. Maybe 1 page on the front or front and back, that you're not flipping through multiple pages. Bring a scrap piece of paper. That way, if you do decide you want to handwrite and take a picture, you have it. Or if you want to scribble calculations that you're going to then type up it explaining in words, but have some scrap paper. Have a calculator just in case. You're not going to really need it, but have it there just in case you do want to graph and look at an equation and what shape it would make or anything like that. Okay, so Roger, you want to take us home?
Yeah, thanks so much, Kristen. That was brilliant. All right, so just a few things before we say goodnight tonight. I want to just kind of touch on a few other items. So let me just share my screen and we'll see where we're going with that. I'm going to, let me come over here. I'm going to go ahead and take you through just a couple of things here I want to show you. So first is the 3 different modes of uploading your exam, and you're going to choose whichever one of these works the best for you. You can copy and paste by typing a response and then just you type it in a Word file or somewhere, and then you copy it over and you hit submit. All right, so they think the best thing for that is side-by-side windows. And I do want to say that please check your technology before. We'll talk about that in a minute. The second option is to attach a document and then click submit. So if you have typed something out and you want to then attach that Word file or PDF, you can click and submit and do that. And the third one, which is probably going to be the choice for math students and chemistry students, maybe physics. You have to decide what works best for you. But this is when you take a picture of what you've handwritten and you send it. Just another word about this. Remember that every single paper that you turn in, whether it's typed or whether it's handwritten, it should have your initials at the top, your AP ID number at the top, and then if you have more than one page, you should number your pages 1, 2, etc. All right, but make sure that that's at the top of each, and you should do that before the exam starts so that you'll be ready to go. All right, a couple more things I want to show you, submitting your response. Actually, you know what I'm going to do? I want to first show you these links, and then I'm going to just show you the exam demo, because this, if you only do one thing, please, please, please do the AP exam demo, because what this does is it's not just for you to get familiar with the platform. That is a hugely important reason to do it. But it's also so that you're checking your technology. Is there something on your computer that's going to prevent the AP exam platform from working? So how do you do that? Well, I'm going to show you. We're just going to go to a new browser here, and I'm going to type cbcollegeboard-org/AP demo. And if you don't remember that, just type AP demo in, you should get it. Now, we're not going to sit here the whole time, but watch what happens. First of all, there's a 4-minute video I want you to watch, but then here's the demo. So you go to the demo, ladies and gentlemen, and you type in practice, okay? And then you're going to go ahead and put in your name, last name, month, day, and then you're going to click I agree to the terms and conditions, and you're going to click continue. Now I can't click continue because I haven't filled this out, but this is going to get you, it's going to see the platform, but not only that, it's going to test your technology. It is so important that you do this before next week and that you practice with this platform so that you feel comfortable with it. Yesterday, here in Sarasota, where I teach, I gave my students a mock through a different platform where the exam I sent them opened up at 9 a.m. and it closed at 9:30, and they had, that same kind of experience. So whatever you do, please give yourself that experience of being in a timed environment, and then having a time where you have to stop and you have to upload, even if you're not done. Even if you're not done, don't worry about finishing every question. Get that thing uploaded so you can move on to the next question, because after 30 minutes, if it is not uploaded, it's not going to get submitted. It will not submit. So if you have questions, please ask your AP teachers. Check the AP website for FAQs and other things. And if you still don't get answers, find a way to email one of us. We'll try and see if we can send it. But we want to help. We want you guys to be ready. Okay. Thank you again so much for showing up tonight and every night that you show up. Don't miss tomorrow night at 6 p.m. Come a little early because Kristen is going to be ready to go at 6. Have your papers, calculator, everything ready to go. Take another mock, and then together we'll be back together again on Thursday night to go over it for you. All right. Again, thank you very much for the hard work that you're putting into learning AP Physics C. It's going to make a difference. Have a great night. I'll see you tomorrow.